Hi, everyone. Thank you for coming. So today's talk concentrates on submodular function heuristic families and net dependent. It's based on our paper written by multiple collaborators, you all know. So just a disclaimer, the talk will be more in a lecture format, which means that I will cover the entire paper with all the proofs. And if you don't follow some technical details, that's okay. Don't feel discouraged. And stop me at any point if you have any questions. I'll try to answer them the best I can. So an example that
Thank you.
Thank you. Okay, great. So yeah, the motivating example that started the project is for fair maximum coverage problem. So here we start with the universe on M elements, and we also have a collection of n subsets. And the objective is to choose at most k sets to cover as many elements as possible. So this is a vanilla maximum coverage problem. And as a real world example, we can think of elements as patients and sets as facilities. So in the beginning, all the facilities are closed, and we want to open k facilities to stay within our budget and serve as many patients as possible. So if for the fairness context, we also are given information about what demographic groups the patients belong to. And for example, if we have some demographic group, like the pink one over here, that are only covered by sets of small cardinality, then it might be that the optimal solution, the final coverage, will not contain those sets, and the elements will not be covered. That's not fair. So along with the demographic groups, we also have thresholds that just corresponds to the fraction of elements in each group that we aim to cover. So let's look at the example for the green demographic group. If the threshold is 3/4, this essentially means that we are forced to cover all of them or choose these red sets. And if cardinality constraint in this example equals to 3, then we're done. This sounds a bit too restrictive because we probably would like to choose this big set on the right to be in our set cover. So to address this, we would allow to relax the fairness constraints and only aim to satisfy them exactly, approximately. So the constraints that can be relaxed would be referred to as soft constraints, and the constraints that have to be satisfied exactly are hard. So in our case, a cardinality constraint is the hard one. So let's formulate this problem more rigorously as an instance of an integral linear programming problem. So if yi stands for an indicator of element I being covered, then our objective is to maximize the number of elements that are covered. And if xj is indicator of set sj being picked, then we know that an element is covered if and only if there is at least one set that covers it. So this is exactly what the second line tells us. Then we also have cardinality constraints, fairness constraints. So this problem as it stands is NP-hard. So we use combinatorial optimization techniques and just relax it to be now an instance of a linear programming problem, which means that we allow our variables to take fractional values between 0 and 1. Oh, yeah, I think it got removed for some reason. Yeah, sorry. For some reason it got, yeah. But yeah, we still have our fairness constraints. Thank you. And so there is now we need to go back and output an actual solution to the problem as to tell what sub-collection of sets we need to choose in our set coverage. And there is no obvious way of converting this fractional solution to the integral one. One naive way would be to just pick each set as j independently with probability xj. But the problem is that very likely we will end up violating our hard constraints, like cardinality constraint in our case. To address this, various dependent rounding techniques were designed that more generally solve a problem of rounding within a polytope, a matroid polytope, where as an input, we just take some point inside of it, and we need to cover it. We need to round it to a vertex. So one nice property about independent rounding is that the solution would satisfy concentration, which means that if our objective was to look at the number of elements that are covered, then with high probability, we will cover a number that is close to the optimal value of this LP, which is the best we can hope for. So we will discuss what concentration results are known for dependent rounding algorithms within the next 5 minutes. But before that, let's talk about why we care about submodular functions. So recall that this is the form of our objective, but maybe we are trying to maximize the number of elements that are covered by every, the number of elements that are covered in every demographic group or a fraction of elements. So that would be an instance of a submodular objective. And more formally, we define a submodular function as a function from on the power set, such that for any input set S, the larger the set is, the smaller would be the benefit of adding an extra element. And submodular functions are very popular in econ because essentially this captures the law of diminishing returns. So we can view the power set as also as a space of 0, 1 n-dimensional vectors. And with that, we would want to consider an extension so that now the input vector x does not need to be 0, 1, but it can the components can be fractional between 0 and 1. One such extension is a multilinear extension that essentially is just an expectation of f on a set where each element I is included in S independently with probability I. Okay, so recall that we considered LP relaxation of our problem. So now our objective would be relaxed to be multilinear extension, right? And now we cannot solve this problem exactly, but we can find an approximate solution with 1 minus 1 over E approximation factor using a continuous greedy algorithm. This is not that important for our purposes, so we'll just brush over the continuous greedy process. And if there is time in the end, I will talk more in depth about the proof of the guarantees for this algorithm. So the problem is that we are within the polytope, P, and we start from point 0. And then we are updating the value of the point along a trajectory defined by this differential equation. And essentially, the idea is to show that at each time step, this derivative is has value at least as much as whatever is left for us to get to opt. Right. So essentially, we have our objective function f, right? So we want to argue that this derivative has value at least whatever is left to get to opt. And then by standard argument, we would argue that we can get 1 minus 1 over E approximation, just because this solution would dominate solution to this differential equation, and would get. Yeah, okay, so going back, let's talk about the historical context that for our results. So our baseline is a celebrated result due to Chernoff in 1952. Everybody here has seen it already. So as an input, we take 0, 1 random variables that are independent. And then let mu be the expectation of some linear combination of xi's that we fix. Right, and then we can upper bound the lower tail of this probability. So then Pankanesi and Srinivasan showed that the independence condition can actually be relaxed, and xi's only needs to be cylinder negatively correlated. Then Chekuri, Vondrak, and Zenklusen showed that the same result would hold when f now is not linear but submodular function, and now mu would be replaced by the multilinear extension value instead of the true mean. Here actually it doesn't matter, but yeah, we can discuss it in a moment. And then we also have this result when xi's are output by a swap rounding algorithm. So here, again, concentration is around the multilinear extension instead of a true mean. And also we have a factor of 1/8 instead of 1/2 in the exponent. Then Harvey and Olver showed concentration of the submodular function when xi's are output by randomized biped rounding. And our result is that we also get the submodular concentration when xi's satisfy weak negative regression, which is another notion of negative dependence that we'll introduce in a moment. So if we can compare our result with Panganes and Srinivasan's, we'll see that we essentially relax the linearity assumption at expense of a cylinder negative correlation, because weak negative regression is a stronger notion than cylinder negative dependence. But actually it is known that one cannot show submodular concentration under cylinder negative correlation. So in some sense, our result is tight. Yeah. Right. So
can you say something about swap rounding?
Yeah. So unfortunately, that's an open question. We don't know the relation between these two algorithms and weak negative regression. Yeah. So let's define the negative dependence notions that will be useful for our later purposes. Okay, so x1 through xn are 0, 1 random variables, and we say that they satisfy negative cylinder dependence when any subcollection of xi's is negatively correlated. Then we also introduce a notion of one negative association. So just negative association is an old and well-studied notion of negative dependence that tells us that for any monotone non-decreasing functions f and g that are defined or supported on two disjoint subsets of indices, essentially the covariance of the product of f and g should be non-positive. And then for one negative association, we say that g only depends on one coordinate, on one xi, and then f, support of f does not include xi. So, and this inequality should hold. And then we also have a notion of weak negative regression that was introduced by Qiu and Singla in 2022. It says that, okay, for any monotone non-decreasing function f, we want the conditional expectation of f conditioned on xi to be a non-increasing function in xi. And yeah, again, support of f does not include I. And for negative regression, again, the generalization goes the same way. Now we have f that depends on, or now we condition on a vector with indices j. Right. Okay. Any questions so far? Okay. So we established the following relationship between 1NA and other notions of negative dependence. So we say, so first of all, in the binary case, weak negative regression and one negative association are equivalent, but in general, that's not the case. And in general, one negative association is strictly weaker than weak negative regression. And let's consider an example that illustrates this. So here, again, this is our definition. And we consider the following example where we have a pair of random variables x1, x2 that take values 3, 0, 1, 1, 2, 2, and 3, 0 with equal probabilities 1/4. So to see that it doesn't satisfy W and R, we can take a monotone function f, which is identity function. And if we condition on x1 being equal to 1, then this forces x2 to be equal to 1 as well. And then the left-hand side is equals to 1. And then same way, if we condition on x2 being equal to 2, then the right-hand side has to be 2. So we see that this inequality aim for in the definition doesn't hold.
I have a question here on the inequality.
Yep, sorry.
I have a question on the inequality. Is it, where is B? Is it on the left-hand side or the right-hand side? There is, I think, a small typo there, but the clarification will help me.
Yeah, thank you. So B needs to be on the right.
Okay, yeah.
It needs to be decreasing.
Okay, thank you. Thank you.
Thank you.
Yeah.
Yeah, okay. So but now let's see why this distribution actually satisfies 1 and A. So for that, we can rewrite the definition of one negative association as this sum. And first, let's notice that because G is a monotone function, the sign of the term in the sum only depends on the sign of this orange term. So in the binary case, summation vanishes because we only can have x to be equal to 0 and y equal to 1. So the sign of the whole expression will be defined by this orange term. And that's exactly, this sign comes from weak negative regression definition. But now in our case, it's not binary, so we actually have the sum. And even though the contribution on this bad pair 1, 2 has a wrong sign, there is enough negative correlation in other pairs of the points so that the whole sum has the correct positive sign, right? Okay. So now let's prove in general why weak negative regression implies one negative association. It's actually also a very short proof. So this is our goal, to show 1 and A. And let's start with defining this conditional expectation function that we know should be decreasing in xi. Now we can expand the left-hand side of the inequality using this newly defined function f. So we observe that because f is a decreasing function and g is an increasing function, by fkj, these two random variables should be negatively correlated. So this means that we can upper bound the expectation of the product by the product of expectations. And then again, go back to our initial notation, and this completes the proof. Okay, so now before proving the theorem, let's formulate the following lemma. So we start with, again, 0, 1, 1 and A random variables. And we define x1 through xn star to be independent copies of those random variables. So their distributions are the same. And then we claim that for any non-negative monotone submodular function f and any negative scalar lambda, we can show the following inequality on the exponential moments. Okay, so we'll use induction essentially the function itself. Yeah, because we actually use heavily the fact that xi's are binary in the proof. So we want, at one step, we want to replace one xi with its copy xi star. So then we will just sequentially replace every xi, and that way we will prove the final inequality. So our goal is just to prove this colored brown inequality for now. Okay, so we start by expanding the left-hand side. So we see that when we only have this term when x1 equals to 1, and we only have this term when x1 equals to 0. So everything's valid. Then let's factor out x1. And this is just by linearity of expectation. So let's focus on this product. We would like to use the fact that x1 through xn are one negatively associated. So we already know that x1 is an increasing function of x1. So we would like to show that the second term is also an increasing function. So to show that, let's again rewrite this a little bit. So the orange part, first of all, this is an exponential function, so it has to be positive. But at the same time, because f is a monotone increasing function and lambda is negative, the whole orange term is decreasing. And then for the purple part, so first it's positive because, or non-negative because f is a monotone function, but at the same time, because it's submodular, it would be decreasing in x2 through xn, right? So then again, using the fact that lambda is negative, we know that the whole thing will be increasing, and it will be less than 0 because we're subtracting 1 over here. So, okay, now we have a product of two values. One is decreasing towards 0, and the other is increasing towards 0. So the product would be a function that's less than 0 and increasing towards it. So this is exactly what we wanted. So now we have a product of two monotone increasing functions. And now we can use definition of one negative association and upper bound this part by product of expectations. So now, because x1 and x1 star have the same distributions, we can just replace one with the other. And because x1 star is independent, we can bring it back into our expectation. So now notice that the second line and the last line look the same, essentially. So we can just reverse the order of the equalities, and we'll get back to where we started from. Just need to replace x1 with x1 star. And this completes the proof. Kishan, what question? Okay. Okay, so now we are ready to formulate and prove our theorem. So again, we have 0, 1, 1 and a random variables, and we want to show that for any monotone submodular function f, if mu naught is the value of the multilinear extension, then we have the following concentration on the lower tail. So actually, because our random variables satisfy weak negative regression, Qiu and Singla, they showed that this implies that the value of multilinear extension is upper bounded by the true mean, which actually makes sense. So actually look at this distribution. We take the true mean, and then it would take the value of the tail, we're getting an upper bound on this, right? And actually, distributions for which this inequality holds, they satisfy some modular dominance. If we have time in the end, we can also talk more in detail about this notion. All right, so for the proof, we again use independent copies of x1 through xn. And let's rewrite it as this telescoping sum. So we define as yi star, or the ith term in the sum. And then let's bound its exponential moment. So this inequality comes from a lemma in Chekuri Vondrak Zenklusen paper. And then the next inequality, I didn't write out the details, but it essentially follows from the fact that e to the x is greater or equal than 1 plus x. So after that, for the lower tail, we can rewrite it again using the exponential function. Then we use the lemma that we proved. So we're going to use Markov's inequality, and then using the lemma that we proved, we can upper bound it by this function, this fraction. Okay, and then this inequality comes from the second line. And then when we use a value of lambda, it's log of 1 minus delta, by the standard argument, we get this form of the upper bound. And then this can be also upper bounded by this exponent. Yeah. So we don't have upper tail here because it's a maximization problem. So we can't, well, we can't really hope to get above this value. So I think that's why. Well, this is the intuition, but then specifically for the techniques, we require lambda to be negative for submodular functions. Okay. Yeah, and then for supermodular, we could reverse it. But yeah, so that's actually what we're going to talk about like next. So let's discuss the setting for read K families. So here we have not necessarily independent random variables x1 through xn, and let y1 through ym be just functions that depend on xi's. So we say that this would form a read K family if every xi is in the support of at most k yj's. In other words, if we look at the dependency graph, the degree of any node on the left corresponding to xi should be at most k. So Gavinsky, Lovatsek, and Srinivasan in 2014 showed the following concentration result. So if xi's are independent and yj's are Boolean functions, then we can get lower tail and upper tail concentration. This is essentially Chernoff bound to the power 1 over k. It's just written using KL divergence. And actually this result is tight, in a sense that if we consider an example of just k copies of each xi, then we can rewrite the concentration of, like, for example, the lower tail of y's using lower tail for 1 through xm over k. And whatever tail we would have on the sum of independent random variables x, that would be that to the power 1 over k. Okay, so and now our result is a lower tail bound on the lower tail if y1 through ym are submodular functions, and bound on the upper tail when they are supermodular. So supermodular is the same as submodular, except for now the law of diminishing returns, like that inequality is flipped. So the larger the set is, the more benefit there would be in adding an extra element. No, it's so marginals means that yeah, here, yes. Yeah, so as actually we don't have to present two different proofs for submodular and supermodular, because we can observe that if f is a supermodular function, that minus f would be a submodular. But okay, yeah, sorry. So this is just a side remark. But before proving this theorem, we'd again need one more lemma. So let f1 through fm be a read K family of just any functions. Yep.
But here you're not talking about some form of negatively associated.
They are one negatively associated. Yeah. Yeah, they're not independent anymore, but now so in Gavinsky et al., these could be any random variables at all. They could be continuous or discrete. In our case, because they're one negatively associated, they have to be binary. Yeah, Boolean. Yep. Okay. So yeah, let's prove this lemma. So we're going to be proving it by induction on n. So base case holds just by Holder inequality. So now let's assume that we have this inequality for n random variables. We want to expand it to n plus 1. Oops. So let S be a collection of indices such that collection of indices j such that fj depends on x1. So we can rewrite this as that product and write it out using a conditional expectation. So essentially now we view this part as just a function on x2 through xn plus 1, right? And because this part doesn't depend on x1, we can factor it out. So now because we can view this part as an expectation only with respect to the distribution of x1, because we think it's a function of the rest. We fix the other n random variables. We can use again holder. And after that, we viewing this as a function on random variables x2 through xn plus 1 can use our inductive hypothesis. And again, using some more algebraic manipulation, arrive to the right-hand side. So this completes the proof of lemma 2. And now we are ready to prove the theorem. So we start again using the usual exponential moments approach plus Markov. So the first line is for a submodular function, and we will take scalar that's negative, and the second line is for supermodular functions and their upper tail. So we can use lemma 1. And again, using independent copies of xi's upper bound this exponential moment. And then we can use lemma 2 because each of these exponential functions, so these functions form a Ricci family again. And okay, after that, we would want to use this bound in here in the nominators of these two fractions, which would give this expression. And then if we look again at the expression within in these brackets, in the parentheses, using standard technique for proving Chernoff bound, we can choose the valid value for k lambda, and this will complete the proof. So we'll get whatever upper bound we get for Chernoff to the power 1 over k. Okay, questions so far? Okay, so let's talk about the continuous greedy algorithm in more detail and why it gives this 1 minus 1 over approximation. Okay, so the reminder of how the algorithm works. So we start from 0 and then we're solving this differential equation. And we wait for a unit time interval, and we would output just the point y at time 1. Right? Okay. So first, let's argue that every point in this trajectory lies within the polytope. So we observe that, okay, so we can rewrite the point of the trajectory as this integral, and each of these points, just by definition of Vmax, lies within this polytope. And this integral then can be viewed as a convex linear combination of points in the polytope. So because it's convex, the whole thing, this whole expression lies in P. And then now our goal is to prove this sequence of inequalities, where V star is just some vector in P that we'll define in a moment. But for now, it's easy to see that the first inequality holds just by definition, because definition of Vmax, because it's chosen to maximize this dot product, right? So now for the last inequality, let's fix x star as the point where optimal is achieved. And then we define V star as just this expression, right? A vector that connects y and wherever we could improve. So we use the fact that f is a monotone function when we look at this, like this expression over here. And because this part is greater or equal than x star, we can lower bound it using monotonicity of our multilinear extension. And this proves this inequality. And then let's focus on proving the last inequality. So here, let's look at the directional derivative of f along vector V star. So we can just parameterize it by xc. And we would use the fact that multilinear extension is a concave function in any direction. And that's essentially what yields this last inequality. Makes sense? Yeah, so this completes the proof of this sequence of inequalities. And now we can expand the we can look at the derivative of f with respect to t, and using chain rule expand it to get exactly the left-hand side of this inequality. And then we use this bound that we obtained earlier, write it down here. So this means that the solution to this differential equation would dominate the solution to this differential equation. And its solution is exactly what would give 1 minus 1 over a approximation when t equals to 1. Right? Okay, and now let's also discuss Qiu and Singla's proof. Yep. Yeah.
Can you give an intuition about? Yeah.
Yeah. So okay, we have our polytope E. So it's downward closed, meaning that for any x that's in E, for any y that's less or equal to x, y. Yeah. So we start from 0. Yes. So we start from 0 right here. And essentially we're trying to say that, so greedy means that we're
Subject to this quality, we want to maximize the capital.
yeah. So we have f.
Excuse me, can I have the only? This concavity.
Yes.
Well,
Yes.
F is a non-negative.
And monotonicity, yeah, we used it in the blue inequality over here. Yeah. So our f, the modular function greater or equal than 0, and
Little f is greater than. Well, find Supermodular, you can just convert it.
yeah, and then we would have to actually take the max and add it. So it would be max minus f, so it is greater or equal than 0. So I don't think that's why that's partially the reason why I kept this, because I feel like it's more elegant. Yeah, so for continuous greedy, so we start with 0. So we're looking at a trajectory of points y of t that are all in this polytope. Yeah, so for submodular dominance, again, the definition is that we just have this inequality holding for any submodular monotone function f. And we want to show that weak negative regression satisfies submodular dominance. So let's do it by first looking at this function. We see that because f is a submodular function, it will be decreasing in x2 through xn. So because this is a decreasing function, by definition of W and R, actually, yeah, I skipped through. We will get this inequality because we're conditioning on a larger value of x1. And then, yeah, we can rearrange the inequality and multiply it by this vector, where x1 is just a marginal of x1, the probability that it takes value 1. And then if you just believe the algebra, we can rewrite this inequality in this form. And after that, so actually, if we look at this part, because we're conditioning on x1, this is exactly the expectation of f point x. So this is what we get. And then we can rewrite this inequality again. And now we're not conditioning on x1 here anymore. So this actually would be an expectation of f if we rounded the first coordinate to 1 independently. So this is x1 star. And then we again can do the sequentially replace each xi with xi star, and we arrive to our final inequality.